A publication in the journal Astronomy and Astrophysics details a discovery by the James Webb Space Telescope. And to get straight to the point, what was found directly contradicts the current models of the formation of our universe.
Exactly. We're talking about a grand design spiral galaxy called Alaknanda. The problem is that it was observed as it was just 1.5 billion years after the Big Bang.
And it was already mature.
Perfect. With well-defined spiral arms, a structure that, in theory, shouldn't exist so early.
All right, let's analyze this. Why is a mature spiral galaxy at this time something so shocking? What is the established model? What was scientists expecting to find?
Well, the standard cosmological model tells us that galaxy formation is a slow, gradual process.
And chaotic, I imagine.
Yes, very chaotic in the beginning. Think of irregular dwarf galaxies merging over billions of years. They accumulate gas, dust, and very slowly, this mass starts to organize itself.
Until it forms a disk?
Exactly. The gas settles there in a rotating disk. And only later, through complex processes, through density waves, do the spiral arms, like those of our Milky Way, form.
And how long should this whole process take?
At the very least, it would take 6 to 8 billion years to reach such an organized structure as the one that was found.
Okay, so the model predicts slow development over ages. And what did James Webb find in Alaknanda?
It found a finished structure when it should have been just the beginning of construction. Alaknanda, with only 1.5 billion years of cosmic age, already shows this complete symmetrical structure with 2 very clear spiral arms.
This challenges the fundamental chronology. It's like finding a centuries-old tree that grew in just 1 week.
The timeline simply doesn't add up.
Let's get into the technical details because that's where the anomaly deepens. What was the size and activity of that galaxy?
Here the numbers get even more impressive. In terms of mass, Alaknanda had already accumulated the equivalent of 10 billion suns and stars.
10 billion. And what about the star formation rate?
That's what's shocking. It was producing new stars at a rate of 60 solar masses per year.
60 solar masses a year. To put it in perspective, how does that compare to our galaxy today?
The comparison is brutal. The Milky Way today forms on average 2 to 3 solar masses per year.
So Alaknanda was operating at a speed 20 times faster?
20 times. And most impressively, the study indicates that half of all its stars formed in a cosmic blink of an eye.
Which would be?
A span of just 200 million years. Current models can't explain such a rapid, yet so orderly assembly.
I wonder what the team behind the study said about this.
The lead author, Hashijin, from NCRA TIRF in India, summed it up very directly. She said, and I'm paraphrasing, that Alaknanda has the structural maturity we associate with galaxies billions of years older.
In other words, forget what you thought you knew.
That's basically it. The discovery forces us to reconsider the efficiency of the physical processes that govern the formation of galaxies at the very beginning of everything.
It's fascinating.
But how is it possible to see this galaxy in such detail? It's more than 12 billion light years away. That's where a phenomenon predicted by Einstein comes in. The gravitational lens.
Cosmic help? Exactly. James Webb had the help of a massive object that's in the way. The galaxy cluster, Abell 27444. The Pandora cluster. Right. The cluster works like a magnifying glass.
That's right. The immense gravity of the cluster bends the space-time around it. The light from Alaknanda, which is much farther away, passes through this curvature and is magnified.
Distorted but magnified, and
in this case, the magnification made Alaknanda appear twice as bright. This allowed Webb to capture not only its existence, but also its detailed structure. Without this natural magnifying glass, it would just be another red and blurry dot.
And the data is reliable, I suppose? Very.
It wasn't just a single image. The observation was made with 21 different light filters as part of the JWST's Uncover and Mega Science surveys.
This provides a wealth of information.
It allowed researchers to estimate with high precision the distance, the dust content, and, most importantly, to reconstruct the star formation history of the galaxy. It's a top-level forensic analysis.
Analyses like this, which confront raw data with established narratives, are not found in superficial coverage. For ongoing access to dossiers that examine what official science tends to ignore, subscribe.
All right. So, here's what's clear. A galaxy that, according to current rules, shouldn't be there. Which brings us to the central question: why? What are the hypotheses to explain Alaknanda? There are two main lines of investigation. The first one we can call accelerated natural growth.
And the second one?
The second one would be an external trigger.
Let's go to the first one. Accelerated natural growth. How would it work?
This hypothesis suggests that Alaknanda was in a privileged location, in a region of the early universe, with flows of cold gas being channeled directly to it.
As if it were being fed by a cosmic hose.
That's right. Instead of capturing gas slowly, it received a constant and dense flow of fuel. This would have allowed not only explosive star formation, but also for the disk to organize itself much faster.
And the spiral arms would naturally form from there.
Exactly, in a much more efficient way.
I see. And the second option, the external trigger?
The second hypothesis is that an external event induced the formation of the arms, probably a gravitational encounter with a smaller companion galaxy.
Another galaxy passed by and nudged it.
The gravitational disturbance from that passage would have created the density waves that form the arms. It's a known mechanism.
It seems plausible, but there's a problem with that idea.
Yes, a significant problem. Spiral arms formed by this interaction, which we call tidal spirals, tend to be
temporary, yes.
They don't last.
They dissipate in a few 100 million years and are usually asymmetrical. Alaknanda's structure looks very symmetrical, stable, and well-established.
Which makes the first hypothesis more likely.
A little more likely, yes. The one about natural growth by gas flows. But it's still something that needs to be proven.
And how do the scientists intend to do that? What's the next step in the investigation?
The next step is to use other instruments. The spectrographs from the Webb itself or the ALMA radio telescope in Chile.
To measure what exactly?
To measure the movement of the gas inside the galaxy. The goal is to map the rotation speed at different points of the disk. And what is this speed measurement going to reveal?
It will tell us if the disk is dynamically cold or hot.
Cold or hot in what sense?
A cold disk is where the movement is orderly, circular, well-behaved. That would indicate stable growth, supporting the first hypothesis.
And what about a hot disk?
A hot disk is more turbulent, with chaotic movements. It could be the crime scene of a recent collision or interaction, which would support the external trigger hypothesis.
I understand. The internal dynamics will tell the story of its origin. That brings me to a broader question. Is Alaknanda a unique case? An aberration?
That's the fundamental question, and the answer, by all indications, is no. It is not an isolated case.
It is part of a pattern. Perhaps the most spectacular example so far of the pattern that the JWST has been revealing. The early universe was much more mature, complex, and structured than our models predicted. We are finding massive galaxies, supermassive black holes.
And now perfect spiral galaxies, all at times when we expected to find only chaos and primitive structures.
What are the implications of this if things happen much faster?
The implications are profound. If galaxies organized like ours could form so early, that means the conditions necessary for life as we know it.
Rocky planets, heavy elements.
Stable galactic environments, all of that may have arisen billions of years earlier than we thought.
This rewrites the timeline, expanding the window of opportunity for life to emerge in the universe.
Overall, the universe may have become a habitable place much, much earlier.
In the end, then, the discovery of Alaknanda isn't just about a galaxy. It's about us, in a way.
No doubt. Each discovery like this not only reveals the universe's astonishing ability to build complexity at a pace that challenges us, Above all, it exposes the fragility of our own knowledge.
Our scientific models are provisional maps.
Provisional maps of a vast and fundamentally unknown territory. Alaknanda is not just an anomaly to be explained. It is a continent that forces us to admit that the map we were using is, at the very least, incomplete.